Right, in this lesson, we're going to have a little look at the following things. We're going to have a look at something called a reaction profile and how that can be used to show the reactants, so things at the start of a reaction, the products, so things at the end, the activation energy, which is something we'll talk about later on, and the overall energy change in a reaction. Then we're going to talk a bit about what this thing called the activation energy is, and it's the minimum amount of energy that particles must have to react. Right, so first up, the example we're going to use is a reaction between hydrogen and oxygen. So hydrogen is diatomic, so H2 means there are two hydrogen atoms joined together. Oxygen is also diatomic, so O2, two oxygen atoms joined together. So first job, see if you can predict what you think you might make in that reaction. Right, so hopefully you predicted that you make water. And if not, then write that down now. So water, of course, is H2O. You will notice there is only one oxygen here, but two here. So this equation needs balancing. So your next job is to see if you can have a go at balancing this equation. Okay, so if you successfully balanced it, there should be a 2 here and a 2 here. So that means there is 2 times 2, so 4 hydrogen atoms in total here. There is 2 times 2, so 4 hydrogen atoms in total here. There are 2 oxygen atoms here. And 2, remember that 2 is 2 times everything in that molecule, so there is 2 times the 1, so there are 2 oxygen atoms on the right as well. And we're looking at this reaction because it is particularly exothermic. Obviously, I'm not going to do the demonstration, but you will probably know that if you take hydrogen and you burn it, because that's essentially what we're doing here, this is the squeaky pop test, or if you were to scale that up, that will make quite a large explosion. Okay, so this thing called a reaction profile, sometimes also called a reaction pathway diagram, basically just shows how the energy varies as the reaction takes place. You can kind of think about this as being a bit like time. So it's the beginning of the reaction at this end and the end of the reaction at this end. Okay, so first thing we do is we draw a line where on this axis, because there's no numbers, doesn't really matter too much, so we'll just put it about halfway up. And this is going to represent the reactants, or the things at the start of the reaction. So in this particular case, of course, oxygen and hydrogen. Okay, let me draw a second line. Notice this line is below the reactants. This is going to represent the products. Okay, so in this case, it's water. So why is it lower? Well, this is an exothermic reaction. So what happens is these things give out energy into the surroundings. So therefore, if they've given out energy, they have lost energy to the surroundings, then the products must be at a lower energy. Right, so then we get a graph that looks a bit like this. So it's not just a straight line here. Now, the reason we get this is because in order for these two things to react together, you have to break the bonds between the hydrogen atoms and break the bonds between the oxygen atoms. And that requires energy. So this energy here is the energy required to break the bonds. Now, you can think of this bit at the top as being like what we call an intermediate or a transition state. So it's something you can't really isolate, but it's at this point that everything will be floating around as the individual atoms. So there are 4 hydrogen atoms, there they are, you've broken all the bonds, and 2 oxygen atoms, there they are, we've broken those bonds. So that is 2 oxygens, to be clear, not 20. Right, so if we want to look at the overall change, right, we can look at this dotted line here. Now, to be clear, this is the energy required to break the bonds, so that's all of the atoms floating around. Now, at that point, they are not thermodynamically stable. That just basically means that they're not happy, if you like. So what they're going to want to do is bond together to get their full shells of electrons. And in that process, so bond forming, that actually releases energy. And notice that that energy released is greater than, so there's a difference, isn't it, than the energy required to break the bonds. And that will always be the case in an exothermic reaction. Right, so if we want to actually look at the overall change, obviously it goes up and then down by the same amount. The overall change is the difference between the reactants and the products. It's obviously a negative change, as you can see that this is higher than this one, so it's going down. And we call this energy change delta, so that's the Greek capital letter delta, which just means change in H. Now, H is a little bit confusing. It's a term called enthalpy, but we don't need to talk about that at GCSE. Right? In actual fact, they probably won't even use that symbol. They'll just call it energy change, I suspect. Right, so other bits and pieces here. This yellow arrow, well, that's the energy required to break the bond. So that's actually the minimum energy required to get this reaction to actually happen. If you don't have that amount of energy, you can't break the bonds, so therefore you're not going to make any water. And that is called the activation energy. Now that is likely to be labelled like this with a capital E for energy and then activation energy. So the activation energy is the minimum energy required to break the bonds. Right, so your next job is to try and do the same thing, but with, instead of an exothermic reaction, an endothermic reaction. So see if you can draw a axis, energy, reaction pathway. Right, don't worry about writing anything actually on the lines. Right, all I want is the overall curve. So reactants here, right, and see if you can work out where the products are going to be. So remember, endothermic reactions take in energy rather than give out. The commonest error I have when I ask for people to do this is a graph that kind of goes down like that. All right, think about how sensible that is. Whatever the reaction is, it's going to have energy taken in to break bonds to start with. So there's always going to be this thing called the activation energy. There is always going to go up at the start. So see if you can have a go at that, and then we'll have a look at the next slide and so it went. Okay, so let's see how we did. So there's your general picture for the exothermic. Obviously, there's the energy change there, which isn't labeled on that one. So the endothermic should look something like this. So there's your reactants. Again, it doesn't matter where you've drawn them on this axis, really. However, the important thing is the first thing is the line goes up because you still need energy to break the bonds. Then it comes down, but not as far. So this time, overall, energy is absorbed, isn't it? So energy is taken in from the surroundings. So that's what happens in the endothermic reaction. So endothermic reactions would always look like this, and therefore the energy change would always be positive from the reactants to the products. Right, so let's just quickly recap the things that we just did in that lesson. First of all, this reaction profile. Hopefully you can now draw a reaction profile for an exo and an endothermic reaction. And it says the relative energies of reactants and products. So relative just means you don't need to put numbers on it. Activation energy, so that's the energy from the reactants to the top of the peak. And the overall energy change is the difference between the reactants and the products. And the idea that these reactions can only occur if there is sufficient amount of energy for the particles to collide, and that minimum amount of energy is what we call the activation energy.